Thanks everyone for joining, and thanks to the Hertz Foundation for asking me to do this talk. I had a lot of fun putting it together. So today I'll talk a little bit about my career, and then I'll end with talking about the power of underwater acoustics to monitor the changing ocean. Next slide. So a bit about me. I did go to West Point, the United States Military Academy. I received a dual degree in engineering, physics, and mathematics. And I was also the first cadet to be invited by Brookhaven National Laboratories. And there I worked on a project concerning accelerator-driven subcritical concept for the transmutation of nuclear waste. So this was a nuclear engineering project where we used a fast protons to also transmute nuclear waste in the shielding around the nuclear reactions. In 1992, I went through the very rigorous interview process, the two-stage interview process, very memorable, and was awarded a Hertz Foundation Fellowship. And this fellowship really changed my life. So the rest of my classmates went off to their operational units, and I was allowed to go directly to graduate school. If I had not had the Hertz Foundation Fellowship, I would not have gotten to go to graduate school right away. So I do want to thank the foundation for the fellowship because it really changed the whole direction of my life. So I went to the University of Texas at Austin because my husband was stationed at Fort Cavazos, and that was a very good physics program that's pretty close to Fort Cavazos. So I got a master's degree in physics at UT in 1994. And I was looking at climate back then too. So I looked at the adsorption and desorption of hydrogen chloride on ice particles, which is an important mechanism for the ozone layer depletion above the Antarctic. So you can see in the picture there, just a picture of the ozone depletion over the Antarctic at the time. Then after my master's degree, I went and served at Fort Cavazos for the Army. I was a shop officer. I ran a maintenance shop. We fixed everything from tanks. That's a picture of a pretty significant tank recovery operation, and all the way from tanks like that to small arms and radios. And then I was a battalion operations officer. So as a battalion operations officer, I planned the defense qualifications. I was the intelligence officer for a 900 soldier maintenance battalion. So when we went out into the field, I was responsible for planning the overall battalion defense. And day to day, my staff of 18 and I would make sure everyone's qualified on their rifle, that if we had to deploy, we had movement plans. We did all the standard operating procedures and everything like that. I really enjoyed my time in the Army, but I did want to get back to physics and math. So in 97, I resigned my commission and I came back to UT to pursue a physics and to pursue a PhD in physics. So what I looked at, I was still kind of looking at surface physics. And this was a basic quantum problem about the effects of alignment on the dissociation of hydrogen on palladium-111, which is just one of the facets of palladium. This is a basic quantum physics type of experiment because you can describe the interaction with the Schrodinger's equation. In 2001, I recognized that I was going to graduate and wasn't really sure what I was going to do. But my advisor mentioned to me that there was a defense laboratory that's part of UT Austin, Applied Research Labs. So I went to a career fair and I dropped off a resume. And about a week later, I was interviewed to look at underwater acoustics research at ARL-UT. So during the interview, I told Dr. Nick Chotiros, who was interviewing me, that I had no acoustics background. And he said, "Oh, it's okay. It's the same wave equation. You'll be fine." Well, it is not the same wave equation, but I learned the acoustic wave equation, no problem. I ended up teaching underwater acoustics at the graduate level for a few years there too. And I became a research scientist there. And then in 2018, I became the strategic programs director. I ran the internal research and development program. I ran the student programs. I also got involved with Task Force Ocean, which I'll talk about in a few slides. And at that time in 2018, the Army was also standing up the Army Futures Command. So given my Army background, I became the liaison for our lab to the Army Futures Command, and that's resulted in a number of projects here, and it's a very good collaboration with the Army Futures Command. And then in 2022, I became the director for one of the 4 technical laboratories at Applied Research Laboratory, the Signal Information Sciences Laboratory. Next slide. There we go. So I want to talk a little bit about the underwater acoustic project work that I did at ARL. This was really fun. I went on 15 field experiments. I had about 25 sponsored projects. Although I was not on the graduate studies committee, I could be the research advisor for graduate students. So I was the advisor for 11 master's students and 1 PhD student in that time. And I worked with the Office of Naval Research, the Naval Oceanographic Office, and ExxonMobil. And I just want to point out some of the fun things that we did. So in the bottom panel, we were looking at imaging tidal fronts. And if you look it's a little bit hard to see, but there's a tidal front in that water there where we have fresh water over the salt water. And as the fresh water overturns, it creates a bubble layer that can be imaged by sonar. But not only do you have a tidal front in that picture, if you look up, you also have an atmospheric front. So that's a 2-front picture there. And some of the cool places that we got to go were like Italy and Elba Island, which is the 3rd picture over. We did a lot of experiments in the Gulf, and we did some off the coast of France in the Mediterranean. Next slide, please. So I was interested not only in field work, but I was also interested in computational work and modeling because I really enjoy math. And so some of the things that I was interested in is acoustic propagation and shallow water waveguides. So if you look at this movie I've got on the top left-hand side, those are 2 fairly shallow water waveguides of just 40 meters in depth. The top panel has a bottom that's rock, and the bottom panel has a bottom that's rock with an overlay of a thin layer about a meter or so of sand. And as the movie starts again, you'll see that just that little layer of sand really affects the propagation. So the first thing that you'll notice is these so-called pathometer returns that bounce back and forth from the source. There's a lot more that's transmitted into the bottom when you have that sand layer in between. So those are a lot quieter. But then as the sound propagates down that waveguide, the modal structure is very different. Whereas when you have that sand layer, you capture a whole lot more modes in the waveguide than you do when you just have a rock. And so you can kind of see mode 2, and that's about it in the top panel. And you see a whole lot of modes with modal dispersion in the bottom panel. And if you just click the slide one more time, another thing that we were interested in is under ice. And like acoustic propagation under ice for, say, understanding acoustic propagation in the Arctic would be a good example. So in this case, we're using a finite element model, and you see the source going, and you can see that the acoustics propagate inside the ice, and they propagate in the water. And one of the things I was kind of interested in is the effect of the shear wave in the ice on the acoustic propagation. And then tying all this with the field work on the right-hand side, we were interested in the effects of bottom roughness on acoustic scattering. So we had this ROV, and we instrumented it with lasers, and then we put a cylindrical lens on the lasers, and we had a whole lot of lines. And the change in the picture of those laser lines projected on the bottom would give us this microbathymetry that you see in the next panel down. And then we can take something like finite elements, and these are just 4 snapshots of an acoustic wave coming from a spherical source and interacting with the bottom. And that would give us information on the decoherence that you would get from scattering from a rough ocean bottom. Next slide. So we also were, that all was for the Office of Naval Research, who are interested in underwater propagation and scattering, but we also work with ExxonMobil. So one of the things that ExxonMobil was interested in is the scattering from multi-year ice keels and first-year ice keels. So if you look at the top right-hand picture, you see the difference in multi-year ice fields and multi-year ice keels and first-year ice keels. So first-year ice keel looks like these blocks here, all the colored blocks. What happens is two ice sheets will run into each other and kind of pile up these blocks on the bottom. If that keel survives a summer, it becomes a multi-year ice keel, and all those blocks fuse together into one big solid chunk. And the big solid chunk was of concern to Exxon because that can destroy their equipment up there. The first-year ice keels are not so dangerous. So they wanted a low-frequency way of looking far out, getting scattering from these ice keels, and being able to tell the difference between first-year ice keels and multi-year ice keels. And I think if you click on the movie one more time, I think you can, that's a time domain finite element. Yeah, if we just go back probably. Oh, that's okay. There we go. A finite element model looking at that, and the return from those and the propagation in the ice are different. And we determine metrics that tell the difference between those two different types of ice keels. Another thing that they were interested in is the detection and characterization of methane plumes. So we did a lot of experimental work with this, and here's me with a few summer students. And we looked at different bubble plumes and looked at both high frequency and low frequency acoustic scattering from the plumes to see if we could detect those. And it was really interesting because the plumes kind of acted as a column, and as the wavelengths are long relative to the bubbles, they would resonate with different frequencies. And so you could have a low frequency way of looking over far distances to determine these methane plumes. Next. Yeah. So as I said before, later in my career, I became involved with Task Force Ocean. So Task Force Ocean was set up in 2018 by the Office of Naval Research, and its goal is to connect academia across the naval research enterprise to the Naval Sea Systems Command, NAVSEA, the operational oceanographic community like the Naval Oceanographic Office, and the fleet end users, so directly to the operational Navy. And there have been like tactical ocean symposia for Task Force Ocean, where I met the commander of the submarine fleet, for example, in the Pacific. And we get to talk to the sailors and the commanders of these sailors and see what their needs are and see how we can help them, protect national security. So here at ARLUT, our task had 3 goals. First, high fidelity interactive sonar simulation and performance prediction in different environments. Environmentally informed signal processing. So if we've got a sonar and we're looking out, how can we understand the environment and mitigate some of those effects? Or how can we detect what environment we're in? And then through the sensor environmental observation, which is just looking through the sonar at ambient noise, for example, and determining what the environment might be. Another goal of Task Force Ocean was workforce development. We've had 5 graduate students over the years go through the ARLUT Task Force Ocean task, and we've had multiple collaborators from across the naval research communities, including the warfare development centers. Our sponsor is Dr. Bob Hedrick, so I want to thank him for all the great work we've been able to do. And if you're interested in Task Force Ocean, that is their website at the bottom. Next. So now I'm the director of the Signal Information Sciences Laboratory here at ARLUT. And CISL is got a very broad research portfolio that supports the Defense Department and the intelligence community. So in addition to traditional things for me in underwater acoustics, we do support undersea warfare and signal processing, but we also do things that support the DoD and the IC at large. So we do things like AI-based cybersecurity, research and engineering. We look at natural language processing for content understanding. We do information management mostly for the Army. We do geospatial sensing. We have our own drone, and we do some satellite work. We do fluid dynamics. We're looking right now at rotor blade characterization, and we have a Mach 5 chamber, so just on the edge of hypersonics. We're looking at quantum information sciences, and we have quantum education. So, for example, that group has developed a high school program that, through the On-Ramps program, is now available to every high school in Texas. We look at systems engineering, and we support the naval environment with systems engineering and hardware infrastructure for combat systems. We do some national security applications for DOE, for example, and we also look at nonlinear and biomedical acoustics. So it's a really fun and broad portfolio. Next slide. So I want to talk a little bit about academic service. So I've done a lot of academic service in my career, and it's really been something that I enjoyed doing, and I feel like it's important to do to give back to the community. So these are just some of the service things that I have been able to do. Everything in bold on this chart is something that I'm doing right now. So right now, I'm on the Ocean Studies Board with the National Academies of Science, Engineering, and Medicine. And as a member of the Ocean Studies Board, I'm also a member of the U.S. Committee for the UN Decade for Ocean Science for Sustainable Development. And I'm also serving right now on another committee that's putting together a report for the Decadal Survey for Ocean Science for the NSF. So we are looking at ocean science priorities and infrastructure for the NSF for 2025 to 2035. And as part of that committee, we have just released a report on scientific ocean drilling. So you can find all of that on the National Academy site, especially if you look at the Ocean Studies Board, because we are the overall board that puts together all of these committees. I've also worked a lot with the Acoustical Society of America. I was the president from 2017 to 2018 and served on the executive council for a number of years. Right now, I'm the chair of publication policy. And I also have been a reviewer. I have not reviewed a whole lot in the last few years, but I really do support and recommend that all of our young people and on everybody in academia really serve as reviewers. I was a guest editor for three-dimensional underwater acoustic propagation, and I co-chaired the Australian meeting in Sydney for the Acoustical Society. So the American Institute of Physics is made up of member societies, and the Acoustical Society of America is one of those member societies. So I served as a representative for the ASA on the governing board of AIP for a number of years, and then I served as the executive committee member as well. I was on the executive committee when we made the decision to reduce the number of people on the executive committee, and that's when I was no longer on the executive committee. As we've been talking here, I've been an interviewer for the Hertz Foundation. I really enjoy doing that. I've been doing that since 2020. I've also been involved with the IEEE Oceanic Engineering Society. I was a distinguished lecturer for a number of years, which was really fun because you get invited to different meetings, and then IEEE will help pay to offset those visits so that we can kind of get the word out to regional meetings of IEEE OES, and again served as a reviewer. And then I was a scientific committee member for a number of small scientific societies, including the International Conference on Theoretical Computational Acoustics and the Underwater Acoustic Conference and Exhibition. And both of these are really, really fun organizations to be part of because the ICTCA, we had meetings, say, in Vienna, and the UACE always has their meetings in Greece. So it's always great to be part of those kinds of societies. So one of the things that, to circle back on the National Academy's work, that we're looking at with the Ocean Studies Board is climate change. So climate change is in the news. Mitigations for climate change, such as marine carbon dioxide removal, is also in the news. You may have seen the Wall Street Journal article that came out this week on marine carbon dioxide removal. So I wanted to talk a little bit with the rest of the talk about using acoustics to monitor MCDR, marine carbon dioxide removal, and climate change. So I'm going to do that for the rest of the talk. Next slide. So in order to do that and think about acoustics for environmental monitoring, I asked around the community of, I've asked a few people in the community for information on projects that I really think are on the forefront of acoustics for environmental monitoring. So I'm going to start with a little ocean acoustics primer, but then I want to talk about a couple other people's projects that, I think are on the forefront of this environmental monitoring. So Jay Yang gave me some information on the passive acoustic listener from Argo, Bruce Howe from Hawaii on smart cables, Megan Ballard and Preston Wilson here at UT gave me information on seagrass acoustics for carbon sequestration. And then Preston Wilson and Matthew Zeh, who's in Nashville, Kentucky, gave me some information on acoustics for ice sheet monitoring. So next slide. So ocean acoustics. So why acoustics in the ocean, and what makes it so great to really look at environmental monitoring for climate change? So here I have plotted the electromagnetic absorption in seawater on the left, and you can see the absorption per centimeter. And if you look across that electromagnetic spectrum, you can see that there is a huge dip in absorption, so it goes further in the visible spectrum. So in the visible spectrum, it kind of makes you wonder if our eyes were developed in seawater. That's a question for another time. But really, blue-green light will go the furthest in seawater until you get to very, very long wavelengths. But it only goes detectably for a few hundred meters at best in blue-green visible light. Now, if we look at that same 10 to the minus fourth absorption per centimeter, and we go to acoustics, and we look across frequencies, we see that we have to get pretty high up in the acoustic frequencies in order to see that same 10 to the minus fourth absorption per centimeter. And there's plenty of frequencies that are below that by orders of magnitude. So what does that mean practically? So go forward. And just to orient you, that one is middle C, and then that's the highest frequency for human hearing, just so you can kind of see what acoustic frequencies we're talking about. So next slide. So what it means is something like this. There is an experiment off a Heard Island back in the 90s where they let out low frequency sound in the SOFAR channel, which I'll describe in just a moment. And they heard that sound on both coasts of the US, in Sri Lanka, in South Africa, in Tasmania, near New Zealand, and Antarctica. So low frequency sound especially can travel thousands of kilometers in the ocean. Next slide. So if we kind of think about basic deep ocean acoustic propagation, it looks a little bit like this. So on the left side, I've plotted the sound speed as a function of depth in meters. And the sound speed is a function of temperature, salinity, and pressure. And pressure is pretty much depth. And what you can see is that there is a nadir for the sound speed at about 1,500 meters depth in this scenario. And this is really common in the ocean. We get this channel here. It's called the SOFAR channel. So at the upper end of the ocean, maybe down to about 1,500 meters or so, you're going to get effect from temperature and salinity. And below that, it's really just pressure, which is depth. So sound is going to turn away from faster sound speeds. And so if we let out sound in the SOFAR channel, it will be contained into the SOFAR channel and travel really far. And that's how they did the Heard Island feasibility test. If we let out sound near the top of the channel, which is the picture that I have on the right, we get a little bit different propagation. So we can get a captured and a surface duct because of the temperature variation in the top, which is the mixed layer. And we can also get it diving down into the ocean like you see this. So this is a way that acoustics is sensitive to temperature and salinity in the ocean. Next. Okay, so it's not just temperature and salinity that we can be sensitive to with acoustics in the ocean. There's other things that we can monitor with it too. So I want to talk about one of these with the passive acoustic listener from Argo. Next. So first, a little bit about Argo, if you're not familiar with Argo. So Argo is basically a NOAA program, but it's also international. And it collects information from the ocean, from these free drifting ocean profiling floats. And they drift with the ocean currents and they move up and down to about 2,000 meters. And they collect all types of ocean data. Next. But what we're interested here is maybe acoustic data. So there's only about 95 of those thousands of Argo floats that are acoustically instrumented. So, but it's ideal for passive acoustic measurements. So this is the kind of thing that the passive acoustic listeners are doing. They're floating just like the regular Argo floats. They go down to about 1 kilometer and they spend 9.5 days at that depth taking acoustic data. Then they dive all the way down to 2 kilometers and then they come up for the sea surface. And they listen between 0.1 and 40 kilohertz and they send that data back, the power spectral density of that data back at 10 frequencies. So there's a picture of what. Next. So these are the locations of the passive acoustic listener Argo floats over the ocean, and we've got about 95 of those right now. Next. And what are they listening for? So here's an example of the spectrogram of one of the passive acoustic listener floats. So first of all, you see on the y-axis, those are the frequencies that they're listening to. So in this case, it's a little bit broader frequency range because it's going up to about 50 kilohertz. And then the color is the amplitude of the acoustic noise, and then the x-axis is time in days. So what do we see here? So we see some background here, and this background here at about day 42.6, that's indicative of drizzle on the ocean. And then the event at 43, and you can see the frequency spectra of light rain followed by a very heavy downpour. So you get the light rain kind of earlier in time, and then the lower frequencies are indicative of a heavy downpour. And then just the background is indicative of the wind speed. So the amount of fresh water in the ocean and the amount of rainfall is really indicative of climate change. Next slide. So next I want to talk about smart cables because it's a really interesting and fun initiative by Bruce Howe at the University of Hawaii. Next slide. So this is Bruce's slide, and his idea is to instrument existing telecommunication cables with acoustic seismic sensors, which are just low frequency acoustics, that you could look for things like geohazards, so early tsunami warnings, but the frequency goes up high enough that you could probably monitor other things as well. So you will get things like the temperature at the bottom of the ocean, you get pressure, you get seismic motion, like I just said. And in addition to Bruce's Smart Subsea Cables initiative, there's a new initiative called Distributed Acoustic Sensing, DAS, which is using fiber optic telecommunication cables, where you can send a light pulse down the fiber optic, which is sensitive to the strain in the fiber optic. So it kind of acts as an interferometer, and based on the strain in the cable, and you can tell where the strain events are happening just based on the timing, you can detect acoustics through through fiber optic telecommunication cables with no additional instrumentation. Next. So I also want to talk a little bit about marine carbon dioxide removal. And one of the big issues with marine carbon dioxide removal is how can you tell that it's actually working? So I want to talk a little bit about seagrass acoustics. Next. So again, I want to thank Megan Ballard and Preston Wilson for this slide. So we can use acoustics to monitor seagrass meadows in two different ways. So passively, we can listen to the seagrass meadows, and they will release bubbles through photosynthesis, and that's indicative of the health and density of the seagrass meadow. So just passively listening, we can hear that. And what you see in the bottom left-hand plot is the diurnal effect of the bubbles. So we have sound level on the y-axis. We have days on the x-axis. When the sun is out, then the seagrasses have photosynthetic events, and you can hear the bubbles, and that's how we can tell the health and density of the seagrasses. The other thing that Preston and Megan are looking at is the amount of carbon that's sequestered in the soil beneath the seagrass. And using an active source this time, they can send active acoustic energy into the soil, and through that, they can determine the amount of carbon that is captured in the soil underneath the seagrass meadow. Next. And then lastly, I want to talk a little bit about passive acoustics for ice sheet monitoring. So next. So it is difficult through satellite to determine everything that's going on with the ice sheets in the Arctic. So one of the things that you can do is just do passive listening. So when the ice sheets melt, they release bubbles, and that the collapse of those bubbles create acoustic noise. And so if you look at the bottom plot, what's plotted there is another spectrogram. So we have frequency on the y-axis and time on the x-axis, and the color is indicative of the amplitude of the noise. And the top band there at about 1,000 hertz, a kilohertz, is indicative of those bubbles that are released when the ice melts. The other thing that happens is that you have calving events where you have a large piece of ice fall off of a glacier or an ice sheet into the ocean. And when that happens, it also creates a lot of noise. And you can see there in the lower frequencies at about 60 seconds or so, a calving event. And through these types of measurements, Matt Zay and Preston Wilson have determined the power spectral density of the ambient noise of these events. And that's what you see in the right-hand plot. So on the y-axis is the power spectral density, and on the x-axis is the frequencies. And that's a normal plot of ambient noise in the ocean. So in the black lines are things that are really well known. So at the low frequencies, those are seismic events like earthquakes or explosions. In the black lines, kind of at the higher frequencies, like around a kilohertz or 10 kilohertz, different wind states will kick up the ocean enough that we already know the spectra of that, what that sounds like an ambient noise under the ocean. So those are sea states. That's just indicative of the wind. But what Preston and Matthew have added are these ambient noise spectra for events like calving, for events like ice melting. And that's going to help us monitor. We can passively monitor those events underneath the water in the Arctic. Next. So just a few parting thoughts. I really want to thank the Hertz Foundation for starting my career. I would not be here today without my fellowship. I also want to thank the Army because my time in the Army set me up for a long career supporting national security, and I really believe in the national security mission. And then I hope that I've gotten across that acoustics is the ideal modality for remote sensing in the ocean. The electromagnetic spectrum does not propagate very well in the ocean. You really cannot use, you can't use GPS, for example, in the ocean. But in addition to key applications to national security, acoustics can monitor climate change and provide insights to things like carbon dioxide removal in the ocean. And I think we're going to add a link in the chat to Marine CDR report from the National Academies that kind of talks about those mitigation methods that I mentioned for Marine CDR. And then lastly, acoustics expertise is a needed commodity. We're a small community right now, but all that acoustic expertise is needed not only by scientists and engineers, but also by policymakers so that we can understand monitoring the ocean and ambient noise abatement. So the National Academies, through the Ocean Studies Board, has a new report called Ocean Acoustics Education Expertise that should be released in a few months, and that's the link to it. Next. So when you're at sea, there's not a lot to do. So you just take a whole bunch of pictures of sunsets because they're amazing. And here's one of the hundreds that I probably have. But I'll take any questions that you might have now.
Great. Thank you so much for the fascinating talk. I'm unfamiliar with this field, and it's always so fun to learn like an entirely new field from such an expert. So let me remind everybody, if you have questions, please put them in the chat. There's a link to a question portal, I think, that Anne and Carla have posted. And we already have some great questions coming in. So let me jump right in. So this question is from Mike Worth, who's a Hertz Fellow. Can you comment on the future of AI in discriminating man-made signals in the natural ocean acoustic environment?
Yes. So this is a question that we get all the time, and it's the area of active research in the lab. So I think that's the issue always is, the data. Everyone talks about AI, but it's always the data. And so in order to do really well with AI, you need well-curated data in a lot of different environments. So AI was developed in very curated ways with, say, images, for example, which you know everything about the image when you start. Acoustics is really different because there's so many different environments. There's so many things that are going on. The acoustic propagation is different everywhere that we go. So what you need is a well-curated, well-understood, well-labeled data set to do that. And I think that in the areas that we have those well-curated data sets, we do really well doing exactly that. But AI is terrific at interpolation and kind of not so good at extrapolation. So in the areas that we don't have that really well-curated data, we don't understand the propagation as well, I think that it's harder.
I'm going to add a follow-up to that. Are there kind of new areas that have been opened up by AI in acoustic research? Has it enabled anything new? Maybe not doing what you're already doing, because that seems hard and, like you said, has challenges with curated data, but maybe there's some new data mining application or something that's interesting.
One of the things I'm really excited about that I see going on all the time is using AI to kind of describe the underwater environment a whole lot better. So one of the problems with the ocean circulation modeling, looking at like the Gulf Stream and eddies and all these big basin effects or anything like that, is the resolution is really too coarse for acoustic propagation. So acoustic propagation in the mid frequencies might be going over like tens of kilometers. I did show the big one, but that was very low frequency. And so when you're trying to use an ocean circulation model to predict acoustics, it's often really, really hard. And then also those ocean circulation models weren't really set up for acoustics. So we also need much finer description of the depth dependence of all those ocean processes to understand acoustic propagation. And that's kind of where I'm seeing a lot of really interesting ideas with AI step in. So the Argo floats are a fantastic set of data. And so you can take the Argo floats and you can kind of compare them to ocean circulation models, and they compare pretty well until you're like missing the surface channel that you were interested in that I showed. So what I've seen some people do is take that and start doing things like k-means clustering on that. And then you can kind of start to see in these Argo floats, these different regions based on just, acoustic propagation, for example, effects. So some things that you're looking at are different from what maybe the ocean circulation modelers are interested in, and all these regions that are really interested. So that is, I think, really a neat new application that I've seen.
Yeah, interesting. Okay, our next question is from Scott Ransom, also a Hertz Fellow at NRAO/VA. Great talk, Marcia, and great to see you. I was wondering if your lab has looked at the effects of acoustics on aquatic mammals like whales, especially human-generated noise. Thanks, and beat me.
Yeah. So Scott and I are classmates. So I've known Scott since, West Point days. So hi, Scott, too. So that area of research is a really active area of research, and it's not really one that we are particularly looking at. Although we do keep tabs at it, and Office of Naval Research has an active research program in that too. I'll say a couple of words about marine mammals. So one of the things that you are concerned about with marine mammals is like the changing behaviors. So it's not just, the big events that people talk about, like the beaching of whales or something like that, but it's more of, are they diving less deep? Are they, foraging differently? Are they, and that is a really active area of research, even though it's not being done at our lab. One of the things that I did see that I thought was interesting is don't forget that it's not just sonar putting sound in the water. Because that's really localized events when, you've got a lot of pinging going on, for example. And it's not just the military. So, first of all, there's a lot of seismic surveys that are done by the oil and gas community, but shipping is a huge source of ambient noise in the ocean. And one of the more interesting talks that I saw at the ASA is that whale vocalizations have changed their frequencies to get out of the band where shipping ambient noise is.
Wow. I'm going to ask another follow-up question, which is related, but are there applications in using acoustics to track aquatic species, migration patterns, or how this species populations change over time?
That is the number one way to do that.
Okay.
It is done all the time. That's a really active area, and it's all done passively. Because of the vocalizations. So as you may know, the Odyssentetes, so the whales with teeth, they hunt with acoustics. So like dolphins, for example, they're not whales, but they do that like dolphins. And then the baleen whales, they use their vocalizations for different things. So really to track marine mammals, because their vocalizations, especially the low frequency ones that the baleen whales use, they will go thousands of miles. And so it's the number one way to track whales in the ocean.
Oh, okay. Next question is from Anonymous. What are the pathways to commercialization for this work? Are there incentives to roll out these methods to society outside of research and military?
Well, that's a good question. I have to think about that. So one of the things that we talk about at the Ocean Studies Board is the commercialization of ocean data. So there's places like Saildrone, for example, if you've heard of them. They go out, they have some spectacular videos of their sail drones and hurricanes that I just saw, which was fascinating. As far as acoustics is concerned, there's already a lot of commercial applications of acoustics. For example, mapping, bathymetry mapping, seismic exploration for oil and gas. All of underwater communications have to be done with acoustics, so there's commercial applications for that. There's fishery applications for acoustics for species monitoring, for example. I mean, there's even acoustics on the nets. It's called a net node, which counts the number of fish coming in. And then there's just commercial applications for fish finding, which you might have used on your own boat if you want to do something like that. So as far as commercial applications for environmental acoustic monitoring, I'm not aware of any of those right now. And there might be commercial applications for evaluating marine carbon dioxide removal, because as you know, there's a lot of commercial companies trying to do marine carbon dioxide removal credits using the ocean. And so how do you actually determine how much carbon that you took out? That's a really, really hard problem. Maybe acoustics might be able to help with that.
Okay, next question is from Kritika Valuri. One, will these slides be available for us? I'll ping that the recorded talk will definitely be available online, and I'll let Marcia speak for the slides. And then two, are most of these issues addressed through research institutes, or are any industries collaborating with research institutes?
Okay, so that's a good question too. So my day job is in defense. So, obviously there's a lot of commercial institutes in defense. As far as like public-private partnerships, which is a little bit separate from the question because she asked about academia instead of like public. So public to me is like more the government. I think that's being determined. So we talked about, the privatization of ocean data. And I think another public-private partnership that could be utilized in the ocean science space is probably data curation. There's a whole lot of very heterogeneous data in ocean science that needs to be fused together, curated well in order to apply new AI algorithms on that. So I think that that's there too. And then as far as like another public-private partnership that might be kind of interesting is instrumenting like shipping vessels with ocean science instruments. So can you instrument a shipping vessel with acoustics, for example? You have to get out of the ship's noisy to start with, but stuff like that. And then we talked about smart cables, which would be another public-private partnership.
Yeah, great. Okay, next question is, you mentioned biomedical acoustics as an area in your lab. I'm curious about the overlap of using acoustics for underwater monitoring versus monitoring the body with something like ultrasound for medical imaging, if discoveries and tools in one field transfer over to the other, or if they're quite distinct.
Yeah, so acoustics is acoustics, which is kind of, there are distinctions, but a lot of the problems are similar. So we have been kind of wondering, what can we do in this field? So we have looked at nonlinear acoustics for, say, kidney stone ablation in the lab before. But one of the things that we're kind of interested in, and we've been talking to Dell Medical and MD Anderson a little bit about this, is more imaging issues. So, say you want to use acoustics to image, say, the brain, then you have to go through something that has a shear wave first, which is your skull, and then the brain itself is going to be more compressional wave. And there's a whole lot of signal processing that has to be done to understand not only the propagation to do that type of imaging, but also what signals do you send and how do you do that type of tomography. And it's important because, like, for cancer research, they've shown that the shear component, so like just the stiffness of the tumors, is really different from the surrounding tissues. So understanding the difference in propagation for example, shear waves would be something that's really interesting to us. So we've been talking to institutions like that about how to share knowledge and take some not only the acoustics expertise, but the signal processing and the information science expertise that we've developed over the years to try to apply to some of those problems too.
Yeah, interesting. I did some ultrasound research early in my academic career, and even just some of the plots and data sets and data processing we were talking about was ringing bells. Okay, so moving on, maybe just time for one or two more questions. This is more specific to one of the projects you talked about with the seagrass, but listening for bubbles from seagrass or ice sheet seems like a very small signal. Do you often get false positives? What causes the false positives and how do you filter them? Are false negatives a problem?
So I will say that I want to thank my colleagues for the slides. So you're going to get maybe a little bit of a non-expert result. So I will try to answer. So one of the ways that we really do determine, these bubbles is that the bubbles do have really high resonances that are in particular frequencies. And so that's really tied to the size of the bubbles. So false positives aren't really a big issue when you talk about bubbles because they are really loud in their resonant frequencies. So even passively, when they collapse, they have a pretty distinct sound. And so if you remember in the ice sheet, when we saw the band for ice melting, that's when you see that spectrum, you can see it. So not so much false positives as much as the noise. So it's always a signal to noise ratio. So if you have a lot of ambient noise, it's going to wash out your signal. So it really depends on how far away you are, the extent to it, the amplitude of the signal that you're looking for, and then the amplitude of the ambient noise.
Let's see. Yeah, I'll do one final question and then we can wrap up. You've been in acoustics research for a long time and worked in climate research for a long time. How have you noticed these fields change over the last 20 years with the evolving urgency and politicization of climate change?
Yeah, that's very frustrating. So I'll answer the climate change one first. So I think that with sea level rise, I don't think even if you're going to deny the word climate change, you're not going to be able to deny the effects of climate change. So you can attribute weather patterns to a whole lot of different things. But sea level rise is sea level rise. And when those tides keep on coming in and they come in higher and higher and higher, like they will be doing, then no matter what you call it, you're going to have to react to it. So acoustics has been around for a really long time. I think that, there's been the newest techniques that I think are exciting are AUVs because that increases our footprint with that. They're challenging. And then, distributed, so I was talking about powered AUVs, but the distributed floats like the PALs and the smart cables, those are all things that I'm very excited about on the forefront of acoustics.
Great. Okay, well, I think we are about at time. I want to thank you again for your wonderful talk and for sharing your experience with us. I think Marcia agreed to stay on for a few extra minutes if there's anybody on with lingering questions. But for those of you who do need to go, I want to throw out a quick few reminders before people sign off. Again, the registration deadline for the summer workshop is tomorrow. Hopefully we see you all there. Second, we have our next innovation hour already scheduled, so please save the date on September 25th at 10 a.m. Pacific time for a talk by Doyne Farmer. He's a Hertz Fellow and Director of Complexity Economics for the Institute of New Economic Thinking at the University of Oxford. And finally, as has been mentioned a few times, the recording for this talk will be available in about a week on both the Hertz website and on YouTube. So with that, thank you all for coming. Thank you again, Marcia. And maybe at this point, we can just kind of open up the call if anybody has additional questions.
Marcia, I'm curious how, I don't remember if you said exactly how you got involved in the Ocean Board, and I did appreciate that we have Kelly here, maybe still, or did have Kelly. But how did you get involved in that during your career?
Yeah, so I'm not exactly sure. I have a suspicion, but I got an email one day and it said, "Hey, we'd like to consider you for the Ocean Studies Board." And frankly, I thought it might be spam. And so I was going to delete it until I recognized that knew the chair, who was Larry Mayer at the time from the University of New Hampshire. And I'm like, I don't think this is spam. So it was a little bit out of the blue. But what happens with the Ocean Studies Board is that board members and the public will recommend people for the Ocean Studies Board. I think it probably was from my work in Task Force Ocean.
That's wonderful. Thank you.
Yeah, it's very fun being on that board. I've learned a whole lot more about ocean science beyond acoustics being on the board, and it really is, it's fun.
I have a simple question, which is for your computational models, how do you validate them? I have this picture in my head of like fish tanks in your lab with rocks and ice and things like this. I don't know if that's true or not.
It's hard to do that in a laboratory setting, although we have tried, because the reflections are a real problem, and then the frequencies don't scale very well. So you go out to sea, and it's not exactly like you compute it. But the modal dispersion that I showed, where you get the low order modes that go faster. I taught this for a long time, so you can stop me when I get too pedantic on it. But that's something that you can definitely see. And so you kind of, take the measurements out, then you come back and you try to model it. So the models can't capture the complexity of the ocean. And the ocean has so much more complexity than the models. So it's not perfect, but that's kind of how you try to validate them.
Do you go out like on the Gulf right there, or are there specific places that are kind of home base for acoustic researchers?
Yeah, it just depends where the ships are. So there's the UNOLs, and I'm not going to even try. I'm terrible at acronyms, remembering them after. But like the UNOLs fleet and the academic research fleet provides vessels, so it'll be a whole scientific party. So it depends on what you want to do. There's these regional class vessels, there's global class vessels. Everything that I did in the Med was with the NATO Undersea Research Center, they have 2 vessels. And one of them is the Atlantis, which, if you remember the Wes Anderson movie, The Life Aquatic with Bill Murray, it was shot on that boat. So that was really fun to be out there on that boat. So in that case, they knew that we had equipment and expertise to come out, and they invited us out on that. And they had another vessel called Leonardo. But getting on vessels and going out to sea to validate these kinds of things is a really big deal. And as you know, Austin is landlocked. And there's a whole history of why we have ocean acoustic research in Austin. I don't know if I have time to go over it, but it's an interesting story. But you get with the other researchers and develop that, and then go out to sea.
What's a good recruiting tactic for grad students? I didn't get to take field trips.
I sent one guy out. I feel kind of bad about this because I sent him out to sea and I couldn't go. And so he goes out there, and he was out there for a week, and he comes back and I'm like, how'd it go? And he goes, oh yeah, it was great. And then when the chief scientist came back, I'm like, how'd my guy do? He goes, oh my God, he was throwing up the entire time. we had to move his roommate out because it was so bad. And so I'm like, okay, I think he's done with ocean research.
Yeah, okay, maybe not a good recruiting tactic. Depends.
Yeah.
Either very good or very bad.
Yeah. Yeah, we also ride with the fleet sometimes, so that's also something that is really fun.